Hi. If you have tried to learn machine learning, you must have heard of Softmax. Even in other contexts, Softmax is a very popular concept. So, what exactly is it? The purpose of this video is to give you a good physical intuition into what is Softmax and why is it used, and also to give you some idea about practical consideration with respect to implementing Softmax. Softmax is basically an activation function. So, the first question that we can ask ourselves is, what is an activation function? Activation functions are used in neural networks to introduce non-linearity. And if we do not introduce non-linearity in neural networks, even if the neural network is very complex with multiple hidden layers or multiple nodes within the same layer, in the absence of these non-linear activation functions, neural networks will essentially be behaving like a linear model. So it will not be able to capture the complexities within the input data. So activation functions are very, very crucial. And there are several popular activation functions. You might have already heard of some of them. Sigmoid is a very popular activation function. It is sigma of z equal to 1 divided by 1 plus e raised to minus z. It goes from the values of this goes from 0 to 1. So if z, which is the x-axis value here, is negative infinity, then this e raised to negative infinity will be e raised to infinity. So 1 by 1 plus e raised to infinity. So that will be a number that is very close to 0. So the left extreme of this function would be 0, which is what is seen here. And let's look at the right extreme. Right extreme would be when z is positive plus infinity. So this will become 1 divided by 1 plus e raised to minus infinity. So e raised to minus infinity is 1 by e raised to infinity, which is close to 0. So this will become 1 divided by 1 plus 0, which is 1 by 1 equal to 1. So the positive extreme of this function is 1. That's what you see here. Tan hyperbolic, on the other hand, has a very similar looking shape, but the values go from minus 1 to 1. So the equation is e raised to x minus e raised to minus x divided by e raised to x plus e raised to minus x. When x is positive infinity, these two terms with negative exponents will vanish. So it will become e raised to x divided by e raised to x, which will be close to 1. When x is negative infinity, then these two terms will vanish and only these two terms will prevail. Then the equation will become minus e raised to minus x divided by e raised to minus x, which will be negative 1. And when x is 0, this will be e raised to 0 minus, so it will be 1 minus 1 divided by 1 plus 1. So that will be 0. So this is the tan hyperbolic activation function. And there is another activation function that's very famous, rectified linear unit, or ReLU. The ReLU essentially looks like a line function for positive numbers. For negative numbers, it's 0. So it's a maximum of 0 or the number itself. So if the number is negative, the maximum among 0 and that number is 0. So for all negative numbers, the ReLU function is 0. For all positive numbers, the ReLU function is the number itself. Now comes the softmax. So the equation of softmax is, if we are given a bunch of numbers, z1, z2, z3, z4, etc. The softmax is e raised to zi, where I is the subscript denoting the index of the number in the array of numbers, divided by summation of e raised to zi, zj, where j runs from 1 to k. K is the length of the array, and e raised to zj is summed over all the numbers in the array for forming the denominator. But surprisingly, it does not have a graph. So let's try to understand what is softmax and why is this used. You may not have understood it even though you may be familiar with this equation. So let's consider a classification problem in neural networks. This is a multi-class classification problem for 4 different classes. Let's say we have a neural network with input layer, bunch of hidden layers, and output layers. We have 4 classes. Class 1 is cat, class 2 dog, class 3 is tiger, and class 4 is rabbit. So this is an image classification problem where a given input image we are trying to classify into one of these 4 classes. And because it's a 4-class classification problem, the output layer should have 4 units. So that's why here you can count 4 of them. For a moment, just ignore what is happening in the hidden layers, input layers, etc. Let's say the neural network is trained and we are feeding the neural network a particular input image of a cat. And the output layer of the neural network may provide some kind of numbers as the output. Let's say this is 3.7, 0.25, 1.1, and 0.18. And this unit in the output layer belongs to the class 1, which is cat. This number somehow signifies cat. This is corresponding to dog, which is class 2. This is class 3, which is tiger, and this is class 4, which is rabbit. So now let's say if someone asks us what's the probability for or what's the prediction here, we can see that since 3.7 is the dominating number among these 4 numbers, we can say that the model is leaning towards cat. So model is essentially saying it's likely that this image is more cat than this being a dog or tiger or rabbit. So what if we want to know the probability of this image being a tiger, or even the probability of this image being that of a cat? We want some number saying for 75% probability this is a cat, with 12% probability this is a tiger, and there is still although this we know as humans, we know this is 100% a cat. A convolutional neural network cannot say anything for 100% certainty. It might say, oh, 0.5% this is a rabbit. It can happen like that. So we want to know the probability of this image being either of these classes. So for this purpose is why we introduce softmax function. So the softmax function is as following: sigma of z equal to e raised to z divided by summation of e raised to z. And here, what is z? Z are these set of numbers. So we have 4 numbers as the zi. So k is equal to 4. J runs from 1 to 4. So let's now plug in the numbers and write the full equation. So for class 1, the softmax of this softmax would be e raised to 3.7 divided by e raised to 3.7 plus e raised to 0.25 plus e raised to 1.1 plus e raised to 0.8. And the denominator for all these units would be the same, because these 4 numbers are the output from the output layer. And when we perform this calculation, the numerator will be same as e raised to whatever this number is. So e raised to 3.7 divided by summation of the exponents. And here it would be e raised to 0.25 divided by sum of the exponents, and e raised to 1.1 divided by the sum of exponents, etc. And this will output a certain set of numbers. Now you must be already be able to notice, let's say you add this equation plus this equation plus this equation plus this equation, then you can see that the denominator for all of these are the same. So denominator you can commonly take out, and the numerator would become e raised to 3.7 plus e raised to 0.25 plus e raised to 1.1 plus e raised to 0.18. So that is exactly same as the denominator. So then it will become numerator divided by denominator will become 1. So what this means is the sum of these 4 equations is 1. So essentially what softmax is doing is it is creating a probability distribution based on the values of these 4 numbers. So here we can see that softmax convert a set of numbers into probability distribution. So the probability that this is a cat is 0.881 or 88.1% probability. The probability that it's a dog, because this node is corresponding to the output dog, class 2, that is 0.028, and 0.028 means 2.8%. Probability that this is a tiger is 6.5%, and for rabbit it's 2.6%. So this is what happens in reality. Neural networks will not be able to say with 100% certainty. There will always be a small chance that other classes also have some the neural network might also predict other classes with some low probability. So of course neural network is completely correct here. This is indeed a cat, and neural network is very confident here with 88% probability. So this is what softmax does. And then the interesting question that we can ask is, why softmax? Why the name softmax? So is there something called as hardmax? So yes, there is something called as Hardmax. Hardmax means it can also be considered as the maximum among the given arguments. So if Softmax, so what? Just look at what Softmax did. So Softmax applied to these four numbers an array of 3.7, 2.25, 1.1, 0.8 resulted in these set of numbers 0.88, 0.028, 0.065, and 0.026. So this was the dominating number, right? The first one was the dominating number. The same principle applies in Hardmax, except the maximum number we assign to 1 and the rest of the numbers are converted into zeros. So a Hardmax applied to the same set of numbers which were in the output layer gets converted to 1, 0, 0, 0. So this becomes like a one-hot encoding. So this is what Hardmax is. And what Softmax is doing is it's actually the transition from one part of the this output array to the another is becoming slightly softer. Here it looks like a step function. So it'll be 1, then everything else will be 0. So the 1 will be applied to whichever has the highest probability. So looking at this probability distribution, if you were to ask what is this image, of course you can say this is a cat because this number is highest. But imagine this number is set to 100% and this is set to 0, 0, 0. So if your requirement is to not give a probability distribution, but rather say this is 100% cat, or you just want to say one thing, then you can use something like Hardmax. But that's basically the difference between Softmax and something like this, which looks like a one-hot encoding. So there is one small practical consideration while implementing Softmax on our computers. If we have a set of four numbers, Z1, Z2, Z3, Z4, it's a common practice to subtract whichever is the biggest number from these four. We subtract that number from all of the four numbers. So if C is the max out of Z1, Z2, Z3, Z4, that C is subtracted from Z1, Z2, Z3, and Z4. So the reason why this is done is to avoid the exponent being extremely huge. So imagine that these set of numbers are 2, 20, 1 and 1000. So e raised to 1000 is like a huge number which our computers cannot handle probably. But so what is done is that 1000 is subtracted from all of these four numbers. And why is this valid? It's valid because subtracting a constant from all the numbers is not going to affect the outcome. And why is that so? If you look at the equation of Softmax, e raised to so let's say we are calculating the Softmax for an array of these four numbers, Z1 minus C, Z2 minus C, etc. So then the Softmax equation looks like this. And from this equation, we can take e raised to minus C out of it. And then e raised to minus C, we can take out both in the numerator and denominator. Then both of them will get cancelled. And then the equation will become something like this. And this is the equation of Softmax for the array of these numbers. So basically, Softmax of these four numbers is same as Softmax of those four numbers minus a constant from all the four numbers. So this is a practical consideration that we have while implementing Softmax. Now let's play a little bit with some example numbers to see how exactly this works. So I have created this Google Sheet with the same four values here, actual values, and those actual values are plotted here: 3.7, 0.25, 1.1, and 0.18. And here I calculate the Softmax by inserting the equation. These four numbers are based on, these four Softmax values are based on these numbers. And here you can see the Softmax distribution. So this is 0.88, 0.027, 0.065, etc. Now let's check one thing. So here what I have done is from this I have, so 3.7 is the biggest number among these four, right? So I subtracted 3.7 from each of those four numbers. So 3.7 minus 3.7 is 0, 0.25 minus 3.7 is this, 1.1 minus 3.7 is this, etc. Now if we calculate the Softmax for these four numbers, these are those values. So you can see in my formula, I have done C2. C2 is this divided by sum of exponent of C2 plus exponent of C3. So C2 is this, C3 is this, C4, C5. So you can see that these values of Softmax calculated on these numbers are exactly same as these values of Softmax calculated on these numbers. So why do we do this? I'll just show you with a simple example. So let's say my actual values are 1, 10, 15, and 1000. You can see that. So my actual values are 1, 10, 15, and 1000. And here you can see that it's not able to calculate the values, and it says numerical value is greater than 1.79 raised to into e raised to into 10 raised to 308. So this is a huge number. And I guess yeah, because this exponent of 1000 is involved in the formula. That's the main reason. But now let's do one thing here. Instead of subtracting 3.7, now we have to subtract 1000 from all of them. Okay, so we subtract 1000 from all of them. So then all of a sudden we can calculate the softmax. Or let me reduce the size of this number, perhaps maybe 800. Okay, so then I can subtract 800 from all of these numbers. And here you see the values now. It can calculate the softmax value. I just want to do one small thing, maybe convert this into 400. Yeah, I guess. And softmax would be, maybe this should be 750, something like that. I just want to see how this could be 751. Yeah, okay, this is perfect. So here, the normal softmax computer is not able to calculate. But if you were to calculate the softmax somehow using a good computer that can handle these big numbers, it should work, right? Because this should be e raised to 1 divided by e raised to 1 plus e raised to 750 plus e raised to 15 plus e raised to 751. And you know that because denominator is so greater than the numerator, the value should be close to 0. And what we have done here is these are the actual softmax for these set of numbers. And how did we do that? What we did is from each of these numbers, we subtracted the maximum number. What is the maximum number? Oh, sorry, this should be, I guess this should be 751. Because 751 is my maximum number. And yeah, so now these are the softmax values corresponding to these numbers, and we are able to calculate it because we subtracted the maximum number, which is 751, from all of those numbers. So why is now the calculation easy? It's because e raised to minus 750 is a very small number that the computer can handle. E raised to minus 1 is a number that the computer can handle. E raised to minus 736, which is again close to 0, is a number that computer can handle. E raised to 0 is something that the computer can handle. But e raised to 750 and e raised to 751 are very, very big numbers which the computer cannot handle. So this is the practical consideration with respect to softmax. You should be aware of while doing the calculation. So it's a very common practice to subtract the largest number from the list of numbers. So what are the advantages of softmax? As we already saw, it creates a raw set of numbers into a probability distribution. And softmax is a smooth differentiable function. So in convolutional neural networks, there is a concept called backpropagation, which allows us to modify the weights and bias. And for that, we need a differentiable function that will be good. So softmax is differentiable. Softmax allows us to perform these multi-class classification while assigning probabilities to each class. So we saw the cat, dog, tiger, and rabbit classification, and it was very, very smooth. It also allows us to normalize the input. So what I mean by that is, since softmax, the sum of each of those numbers should be 1 because it's a probability distribution. Even if the input numbers are huge and ranging from minus 1000 to plus 5000, all those range of numbers can be brought down into a range from 0 to 1 as a probability distribution by softmax. So it can normalize the outputs, preventing numerical issues. So how does it prevent numerical issues? Those big numbers can be brought down by softmax. And it also provides interpretability because the higher the softmax value, it is somewhat correlated with the probability of prediction of a certain class. And softmax is also compatible with the cross entropy loss, which is very commonly used during the training process. So that's all about softmax, and hope you understood some things, and when you try to implement, please keep these ideas in mind. Softmax is not a difficult concept. It's a very simple and elegant concept. So thank you so much, and we'll see you in the next video.